All psychological research involves collecting measurable data and analyzing it in an objective way, as we discussed in the previous video. However, there are different types of study designs that researchers can use to collect that data in the first place. In particular, in this module, we'll discuss 3 basic types of study designs: case studies, correlational studies, and experiments. In this video, we'll discuss just the first 2, case studies and correlational studies, and in the next video, I'll cover experiments. One way to collect data is simply to study 1 or 2 individuals in great depth. This is called a case study. This method may be helpful if the condition that a researcher is studying is relatively new, poorly understood, or just very rare. For example, for many years, psychologists studied a man named Henry Molaison, who had had a part of his brain called the hippocampus removed in an attempt to control debilitating seizures that had not responded to medication. At the time of Henry's surgery, psychologists still didn't really know what the hippocampus did. However, in part thanks to Henry, we now know that the hippocampus plays a crucial role in converting short-term memory into long-term memory storage. After Henry had his hippocampus removed, he was no longer able to form new lasting memories. Psychologists studied Henry closely for many years after his surgery and learned a great deal about memory through their observations of him. A benefit of case studies is that they often tend to collect very rich, informative data, and they can also be used to study rare phenomena where it is difficult to gather large numbers of participants. At the same time, however, because they only study 1 or 2 individuals in depth, it's often not possible to generalize the results of a case study to the broader population. For example, Freud often used case studies of clients to draw wide-reaching conclusions about how he thought personality worked in most people. However, as I already mentioned, many of Freud's ideas are no longer supported today. Had Freud made an effort to study more people, perhaps his conclusions would have been different. Correlational studies, in contrast, typically collect data from a larger sample. In a correlational study, the researcher measures where people score on 2 or more variables. As an example, let's say we're interested in the relationship between exercise and sleep quality. We could get a sample of 300 participants, and for each person in our sample, we could collect data on their exercise habits and quality of sleep. For example, to measure exercise, we could have participants wear a daily step counter, and to measure sleep quality, we could ask participants to self-report how many hours of sleep they get each night and how rested versus tired they feel during the day. After collecting this data, the researcher would need to run a statistical test to compute a correlation coefficient. Depending on the type of data we collect, there are a couple different correlation coefficients we might use, but the most common one is Pearson's R, so that's what I'll focus on in this video. An R coefficient is a number that ranges from -1 to +1, and it tells us 2 key pieces of information. First, the sign, positive or negative, tells us about the direction of the relationship. In a positive correlation, this means that 2 variables move together in the same direction. In other words, as one variable goes up, the other variable tends to go up too, and vice versa. As one variable goes down, the other variable tends to go down too. For example, we would probably expect our exercise and sleep variables to have a positive correlation. The more people exercise, the better we expect their sleep quality to be. And conversely, when exercise goes down, sleep quality might go down too. Another example of a positive correlation could be class attendance and academic performance. It's likely that these variables share a positive relationship. The more classes students attend, the better they are likely to do in the course, while students who skip many classes are likely to get a lower grade. When the R value is negative, this means that the 2 variables share an inverse relationship. That is, as one variable goes up, the other variable tends to go down, and vice versa. For example, hours spent practicing a musical instrument and number of mistakes likely share a negative relationship. The more you practice, the fewer mistakes you'll make, and vice versa. Another example might be the expected correlation between social media use and mental health. When social media use is higher, mental health might tend to go down, whereas when social media use is lower, mental health might tend to go up. I want to quickly note here that once again, the terms positive and negative have nothing to do with being good or bad, so don't get tripped up by that. The second piece of information the R value tells us is about the strength of the relationship, and that is indicated by the number value itself. Numbers close to either positive or -1 represent a stronger relationship, whereas numbers closer to 0 represent a weaker relationship. So what do I mean here by the words strong versus weak? I mean how consistently the two variables move together. In a perfect correlation of positive or negative 1.0, this means that the variables move in perfect lockstep with one another. In other words, increasing or decreasing the x variable by 1 unit always increases or decreases the y variable by the same amount. For example, if you are paid $13 an hour, then the number of hours you work and the gross amount of money you earn will share a perfect relationship, where each additional hour you work earns you exactly 13 more bucks. No more, no less. But these kinds of perfect relationships are very rare in the real world because it's very rare for an outcome to be perfectly or solely determined by just a single other variable. On the flip side, a correlation at or very close to 0 means that the two variables don't share a consistent or predictable relationship at all. For example, there is probably no discernible relationship between intelligence and favorite ice cream flavor, so if we were to conduct a study looking at these two variables, we'd probably get an R value pretty close to 0. In psychology, we tend to observe correlations that range from about plus or minus 0.10 to plus or minus 0.40. An R value closer to 0.10 is considered relatively small or weak, whereas in psychology, an R value closer to 0.40 or higher would be considered fairly strong. And that's because in psychology, the types of variables that we observe are usually determined by many different factors, so it's pretty rare to get a correlation higher than 0.4 or 0.5. Here is some data with a correlation of R equals 0.15. Let's imagine that these are the data we get from a correlational study looking at exercise and sleep quality. And this is actually pretty close to a correlation that was observed between these two variables in an actual recent study conducted by Wang and colleagues. You'll notice that although there does appear to be a positive trend, such that people who got more exercise reported better sleep quality on average, there is also a lot of variability. Again, this is likely because while exercise and sleep quality are related, sleep is affected by a lot of other factors too. Let's do a couple quick application practice questions now together. Which of the following is an example of a negative correlation? The correct answer here is B. The more you sleep, the less tired you feel. This is because these two variables move in the opposite direction. When sleep goes up, tiredness goes down, and vice versa. The variables in answer choices A and C both move in the same direction, so they have a positive correlation. When study time goes down, exam performance goes down too. And when coffee consumption goes up, alertness goes up also. Okay, question 2. Which of the following correlations is strongest? The correct answer here is D. R equals negative 0.78. Remember that the sign of the R value, positive or negative, simply indicates in which direction that the relationship goes. Do the two variables move in the same direction or the opposite? But a negative correlation can still be very strong, such as the correlation between outdoor temperature and heating costs. If you've ever had to pay an electricity bill before, you know that these share a very strong, predictable negative relationship. The lower the outdoor temperature, the higher your heating bill tends to be. After conducting a study and calculating an R value, the next step, as you'll recall from our previous video, is to calculate a p-value to determine if this relationship is statistically significant. That is, if there really is a true relationship between these two variables, or if the result we got was simply due to chance. Let's say that here we get a p-value of 0.004. Recall that this would be considered statistically significant. So even though the effect isn't huge, because the R value was on the smaller side at 0.15, there does appear to be a significant or real relationship between these two variables. So can we say that getting exercise will cause you to get better sleep? Here's where we have to be a bit more careful. Remember that answering this question about causation depends on the type of study design. Here, we did a correlational study, which means we simply measured both variables as they naturally occurred. And we'll see how this is different from experiments in our next video. When we do a correlational study, we actually can't make any definitive statements about causation. In other words, we know that these two variables are related, we just can't say anything about why. That's because correlational studies have two main drawbacks. To say that one variable causes another, we need to show two main things. First, causes always have to come before effects. That's the definition of a cause, after all. So if we want to know if one variable causes another, we need to know which one happened first. Second, we need to show that there are no alternative explanations for the observed relationship. And it turns out that in correlational studies, we have a really hard time doing either of these things. First, in correlational data, when we simply measure two variables together at the same time, it's often impossible to know which one came first. This is called the reverse causality problem. For example, in our exercise and sleep study, we might assume that the exercise came first. But it's equally possible that the causal effect here works in the opposite direction. Maybe people who got better sleep were less tired, and so they were more motivated to go on a walk or go to the gym after work or school. In this case, the two variables are still related, but it's actually better sleep causing more exercise instead of the other way around. A famous example of this in psychology is the relationship between self-esteem and grades. For many years, a positive correlation was observed between these two variables, which led many people to assume that boosting self-esteem would automatically increase someone's academic performance. But longitudinal and experimental studies have shown that it actually probably works in the other direction. When people excel at something, such as school or sports, this causes a boost in our self-confidence and self-esteem. But raising self-esteem on its own is unlikely to translate into better performance. A final example where this is particularly relevant today is the relationship between social media use and mental health. It's often assumed that social media can negatively impact our mental health, and I admit I'm definitely in that camp. But some people argue that it's also possible that the relationship could work in the opposite direction too. Perhaps people who are already anxious and depressed spend more time scrolling on social media because they don't feel like going out and doing other things. In other words, it could be that the poor mental health is causing the increased social media use rather than the other way around. Second, it's also possible that neither variable caused the other, but rather that both are caused by a separate third variable, which we call a confound. To see how this works, let's look at another example. In the 1950s, before the advent of an effective polio vaccine, researchers found a correlation between polio and ice cream consumption. So if you were a parent in the 1950s, should you be concerned about your child eating ice cream and potentially catching polio as a result? It turns out not, because there was a third factor at play here, the outside weather. In the summer, it turns out that the warmer weather promoted transmission of the polio virus. And in the summer, guess what? People eat more ice cream too. So it wasn't that ice cream caused polio, or even that polio caused people to eat more ice cream, rather both were caused by a third variable, the weather. This is known as the third variable problem, and it's another reason why we have to be careful about correlational data. Sometimes two variables look like they are related, but it's only because they share a mutual relationship with some other third variable. As another example, in our sleep and exercise study, it's possible that exercise doesn't cause you to get better sleep, or that better sleep causes you to get more exercise. Instead, having a busy schedule could be a third factor or confound here that explains both. Maybe people with busy schedules just simply have less time, both for sleep and for exercise. So perhaps the busyness of someone's schedule is really the true cause. Let's do one last application question before we close. Can you think of a confounding variable in our social media and mental health example? There are several potential right answers here, but one potential confound could be generational differences. Social media is more popular among younger versus older generations, and mental health issues also tend to be higher for younger versus older adults, for reasons that psychologists are still trying to explore today. It could be that other generational or historical factors apart from social media use, such as economic conditions or parenting styles, are causing the poor mental health, and then the fact that younger generations are also using social media could just sort of be a coincidence. A quick note, to be a confound, a variable has to cause both of the other variables in our study. So for example, genetics is not a confound here. While genetics might play a role in the development of mental illness, and that's a complicated question that we'll explore more in the final module, it's unlikely that the same genes that predispose someone to develop depression would also cause them to spend more time on social media. So in sum, correlations can give us hints about what is happening, but correlational data can never definitively speak to the causal direction between two variables. So we always need to be careful not to infer causation from merely correlational data. For more examples of correlation-causation mix-ups, you can check out the supplemental videos on the Canvas site. In this video, we covered case studies and correlational studies. For the exam, you should be able to define case study and identify in an example, define correlational study and identify in an example, distinguish between positive and negative correlations, given an R coefficient, interpret both the strength and direction of the relationship, and define the reverse causality problem and the third variable problem, and identify how each could play out in an example.